All right, let's get into it. Today, we're going to trace the story of the big ideas that power all of artificial intelligence. We're going to start with the simplest little spark of an idea and take it all the way to the absolute cutting edge, and even into some pretty controversial territory. Okay, let's dive in.
So here's the game plan. We've got 5 main stops on our tour. First, we'll look at a single simple learning machine. Then, we'll zoom out to the algorithms, the recipes that make them powerful. After that, we'll check out the real-world tools developers use, then explore a wild new way of looking at data. And we'll wrap it all up with the big debate about quantum AI.
So let's just start with the most basic question you can ask. Forget about the huge, complex AI models for a second. How can a machine, at its core, learn anything at all? I mean, how does it even start? Answering this one question is the key to, well, everything else we're going to talk about.
Our story starts at the very beginning, at the microscopic level. We're talking about the one simple idea that is basically the great-great-grandparent of every neural network out there today.
Okay, so say hello to the Perceptron. This is pretty much the simplest form of a neural network you can imagine. Just think of it like a single cell with one job. Make a simple yes or no decision. Is this a cat or not a cat? When it guesses wrong, it just slightly adjusts its internal settings. We call these weights, which are kind of like little dials. A tiny nudge here, a tiny tweak there, all to try and get the right answer the next time around. That's it. That's the core idea of learning right there.
Now, here's where it gets really interesting, and maybe a little counterintuitive. For this simple perceptron, how fast it learns, the learning rate, doesn't actually change what it ends up deciding. The line it draws in the sand depends on the direction it's pointing, not how hard it's pushing. So learning faster doesn't make it smarter, it just makes it more confident, I guess you could say. The final conclusion is going to be the same.
Okay, so a single neuron is a great starting point, but you can't build a skyscraper with just one brick, right? So now we're zooming out from that single neuron to look at the big architectural blueprints, the algorithms that actually tell our computers how to think.
These are the heavy hitters. These are the powerful strategies in any programmer's toolkit. Now, they aren't just for AI, they're fundamental to computer science, but they provide the logical backbone that makes truly complex AI possible. Each one is a totally different way of tackling a hard problem.
And this slide just lays out 2 of those strategies beautifully, because they're complete opposites. On one side, you've got recursion. It's a top-down approach. It looks at a huge problem and says, okay, I can solve this big thing if I can just solve a smaller version of the exact same thing. On the other side, you have dynamic programming, which is bottom-up. It starts with the tiniest little piece of the puzzle, solves it, saves the answer, and then uses that answer to build up step by step to the final solution. 2 different paths, same destination.
So we've got our single neuron and we've got our big picture algorithms, but how do we actually connect the two? How do you turn these ideas into something that actually works? Well, that is where frameworks come in.
You can think of a framework like TensorFlow as a massive industrial-strength toolkit. Instead of having to build an engine, wheels, and a transmission from scratch every time you want to make a car, you can just grab these high-performance, pre-built components off the shelf. It lets developers use all those powerful algorithms to build models for all sorts of things, tables, images, text, without having to reinvent the wheel every single time.
And the whole process follows this really clear 5-step life cycle. First, you define the architecture. That's your blueprint. Then you compile it, which is basically setting the rules of the game, how it knows if it's winning or losing, and how it can get better. Step 3, fit, is the main event. That's the actual training. Then you evaluate it, you give it its final exam, and finally you let it loose to make predictions on totally new stuff it's never seen before.
Up to this point, we've kind of been assuming that our data is made of simple, neat connections. But the real world is messy, right? It's complicated. So what happens when a single connection involves more than just 2 things?
And this is where the idea of a hypergraph is just so cool. A standard graph is perfect for modeling a one-to-one link, like a phone call between me and you. But what about a group chat with 10 people, or a work email sent to a whole team? A hypergraph can actually capture that. It models a single connection that links many different points all at the same time. Now, I know this diagram looks a little bit intense, but the core idea is actually pretty simple. It's showing us how a system can see relationships that go beyond just A connects to B.
It can understand a single event that connects A, C, and D all at once. There are even special AI models called hypergraph neural networks that are designed specifically to learn from this kind of rich, overlapping data. And because of that, they can spot patterns that a simpler model would just completely miss. It's a great reminder that our tools have to evolve to see the world as it really is.
All right, this brings us to the very edge of what's possible and what's practical. What happens when you try to merge the learning power of AI with the mind-bending computation of quantum mechanics? Well, it turns out the experts are having a pretty heated debate about it.
So, on one side, you have the true believers, the visionaries. Companies like IonQ are arguing that we are right on the verge of a quantum inflection point. They're saying that just like ChatGPT seemed to come out of nowhere and change everything, quantum computing is about to do the same thing for AI. It's a promise of a total revolution.
But then you get the reality check. Experts like Filippo Vicentini are pointing to this massive fundamental bottleneck, and that is getting data into and out of a quantum computer is painfully slow. It's a huge practical problem that really puts a damper on all that revolutionary hype.
So let's just lay it out, side by side. The promise is that we can enhance analysis of really complex data. The reality? We're dealing with the input-output speed of a desktop computer from the year 2000. The promise is this amazing synergy that will revolutionize language models. The reality right now? AI is mainly being used to help design and run the quantum computers themselves. And while some people are calling for a quantum inflection point, the actual mood at major quantum machine learning conferences is apparently on a downward trend.
So where does that leave us? Well, the consensus that seems to be forming right now isn't about some grand fusion. It's something much more practical. The idea is that AI and quantum computing will be complementary tools. They're both powerful, highly specialized instruments in a developer's toolbox, working side by side but not becoming one single all-powerful thing.
And really, that's the big question for the future, isn't it? We've gone all the way from a single, simple learning neuron to this massive debate at the very frontiers of physics. So as we move forward, will these two incredibly powerful fields finally come together and create a truly revolutionary partnership? Or will they just remain powerful but ultimately distant cousins? I guess only time will tell.